Hello, everyone. This is Elisa Baum. I'm GridGain's Director of Product Marketing. We will begin in just a moment, but first I'd like to conduct a bit of housekeeping. If you could please raise your hand located in the GoToWebinar control panel to let me know if you can hear me, that would be fantastic. Can you hear me? Let's see here. Yeah, I see hands. Fantastic. Thank you. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on GridGain's blog. I will also be sending the questions to Percona, and they'll be doing some follow-up as well. In addition, a recording of this webinar will be made available to everyone within 48 hours. I would like to thank you for attending today's webinar, Accelerate MySQL for Demanding OLAP and OLTP Use Cases with Apache Ignite. This webinar is being jointly presented by Nikita Ivanov. He's GridGain Systems CTO and Co-Founder, and our very, very special guest star, Peter Zaitsev, who is Percona's CEO and Co-Founder. Peter will be kicking the discussion off, and he'll be followed by Nikita, and then both of them will take your questions. And with that said, I'll turn the floor over to Peter. Go ahead, Peter.
Yes, hello everyone. Good morning, afternoon, or whatever time of day it is in your part of the world. So we'll talk about a few things today. We'll talk about the problems which exist in various MySQL-powered applications, which you commonly see in practice, existing solutions which you also see commonly deployed, and also we'll look into the power of Apache Ignite. First, I wanted to share my conviction with you. I truly believe that when it comes to technology, there is no silver bullet out there. It's all a question about the different choices. And why is that? Well, actually, it's very simple, right? When you make a design decisions for any solution architecture, you have to make a choices, and all of those architecture and implementation choices, they have benefits and drawbacks. For example, you can say, well, keeping the data in memory for its access is very, very fast, but then you will be a limited amount of memory, amount of data of memory you can keep in a single system's memory, right, which can be expensive. Now, if you look at the modern applications, especially the large-scale applications, you will see when it comes to a data store, they tend to use technologies, not technology. Right? Typically, that will be more than one technology used on the data layer. And if you look at the largest applications, largest systems out there, such as the Facebook, for example, you would often find what inside they use 10 or even more of both existing open source custom-made solutions to store and process the data more efficiently. That makes sense, of course, right? Because the larger environment you have, the more it makes sense to pursue the most optimal solutions which exist out there. Because if you are operating on your small scale, if you can improve your application's efficiency by 10%, right, or save off 10% of the cost, that doesn't matter that much. But if you are operating on an extremely large scale, then even those single percent may amount to many millions of dollars of a cost savings through years. Now, I think that is especially works well with the open source. Well, why? Because if you choose to use more database components coming from open source environments, they usually don't have hefty license fees which come to that. And even in the cases where you choose to use subscription-only enterprise software version, then it also makes it very easy for the development team to prototype and to check things out whether they work or not without having to engage the sales team and go through evaluation process, which I know is not appreciated by many developers, right, and introduce a friction in the process. I also think it makes a lot of sense in the open source community, because open source community is very good at building bridges. And what I mean by that is by finding a ways how different components can operate together. How you can use this different technology from programming languages, how you can move your data around, and so on and so forth. So, for example, even if there is no official way to get your MySQL data from, let's say, through binary log to Kafka, well, there are a number of open source projects which appeared in the open source community to handle this need. Now, I would warn you, though, what I believe the balance is needed here. You should use many technologies which make sense for you, but do not use more the technologies when it's absolutely necessary, because every additional technology comes with introducing complexity and additional cost in terms of somebody being either in-house or external vendor having that excellence and expertise for you to support that technology. I think that is a very important item to consider. And over years, as I see we have a lot of great open source technologies, I see a lot of mistakes being done by introducing too many technologies which offer little benefit compared to each other, but that gets a substantial increase in complexity. Now, going back and talk to MySQL, I believe MySQL is not an exception. MySQL is great for many things, but it's not really great for everything. And I am actually very glad what right now the situation is different than it was, for example, 10 years ago or 15 years ago. Then we would be doing a lot of stupid stuff with MySQL, which we don't have to do it right now. Right? You would write the scripts to use MySQL, for example, as Hadoop, or try to use MySQL for caching the data, which didn't work so well, and so on and so forth. So what are the problems which we see constantly where MySQL is good to be supplemented by some other technologies? This is the list. It's hot data, highly volatile data, large data volumes, analytical processing, and a full text search. Let's look into those more specifically. First is dealing with hot data. The most typical example of your hot data is your cache, right? Typically, when you have your data set, not every the data piece is accessed at the same frequency. Some will be accessed more frequently than others, and they cause those things hot. And often, it makes sense to keep them somewhere else than MySQL. Typically, when you speak about those cache, you are dealing about the large volume of relatively simple requests. In many cases, we are speaking about hundreds of thousands or even millions of requests a second. And if this volume, MySQL doesn't work very well because the SQL gives you relatively high overhead, right? If it's many simple lookups. Also, when I speak about cache, we would like to see some the data to be in memory, because memory access is the fastest. And in MySQL do not really have a very good memory-focused storage engine. Yes, you have a storage engine called memory, but that is not really designed as for high concurrency. And you also can use InnoDB in memory, but that will be quite expensive if all the transaction support and login overhead it works. Now, what you also find out with MySQL, it's not designed very well for high concurrency. For example, if you have tens of thousands of applications here hitting the MySQL concurrently, you may get exposed to some bottleneck and periodic performance issues. What do we have in terms of solutions? Well, in both cases, I will be talking about solutions how to make MySQL better, because remember, if you can avoid, in your case, to introduce another technology, you probably should do that, as well as external solutions, which typically are deployed at a large scale. When the pain is too large, right, or the gap in capacities is so large, it cannot be used at the MySQL layer. The examples here for on MySQL level would be if you're using memcached interface, which allows to cut a lot of that SQL level overhead, or use a thread pool, which is available as a MySQL enterprise feature, or it's also available in as an open source implementation in Percona server. In terms of external solution for caching and other hot data needs, we very commonly use Memcache D and Redis, those two applications, which I'm sure you at least heard about. The second issue is highly volatile data. What I mean in this case is when you have a lot of updates. Let's say you have many updates go into a single row. For example, something like if you need to maintain the accurate counters, and in some cases those counters change by tens or even 1,000 items a second. For example, good example would be the flash sales. When you get, let's say, some products or tickets online, right, and everybody's trying to grab them by often thousands a second, and you absolutely need to maintain the exact value, right, because so you don't oversell. The reason for that is what MySQL has been really designed around full transactional semantics with support for long transactions, for your relational database semantics. It works with disk-based log durability and pessimistic lock-in. Those all things, they really allow you to get a decent amount of writes, but they're not very well suitable for very high volatile, very volatile data. In terms of MySQL side, there are various solutions which come to the data design. So, for example, we can, instead of maintaining counter in the single row, we can split that and have a counter maintained over a few rows, right? Then you get the random row being updated for different when you need to increase the counter. Such solutions, even though they are ugly, they work pretty well. In many cases, you can also get a lot of mile getting your better configuration. With well-configured MySQL, especially for those things for highly volatile data, can you get up to 10x better performance than your stock MySQL configuration. So don't really ignore that. And the last important thing is using parallel replication. In many cases, dealing with highly volatile data, the problem with MySQL would be that you can do changes on the master, but replication will become bottleneck, and your replica just would never be able to keep up. That problem is solved now with a parallel replication in MySQL 5.7 as well as Percona X-Ray cluster. In terms of external solutions, I would say the Memcache and Redis are being very commonly used solutions to supplement out there, as well as we see folks using other technologies such as Cassandra or Memcache with a whole different data model and moving the primary data store to those systems. The next issue is our large data volume. So what is the data volume problem? Well, MySQL itself was originally designed as a single node system. It was not designed for the modern concept of your data center is your computer, right? And everything kind of supposed to run on a multiple node, and single node shouldn't even matter. Well, that wasn't the case when the MySQL was started. And because it's designed for, firstly as a single node system, it's kind of limited in CPU and memory resources in terms of how much volume that single node can help. Of course, if you look at any large MySQL installation, right, being again, whether it's Facebook, Twitter, or any other countless huge MySQL installations out there, they are not using MySQL as a single system. Of course they don't. They are using sharding. But sharding solutions in MySQL are manual and quite painful, especially if you have some complicated queries which have to query the data among the different shards. It becomes complicated. In terms of solutions, well, as I mentioned, we can use, well, pretty much sharding is the only game in town, right? I mean, if you have a large data volume, you have to partition, shard, whatever you want to call that term, and place it across multiple MySQL systems. Now, in many cases, that's done manually on the application level, which is not great, but that worked for many teams out there. You can also use such solutions as a VTES, which is a framework YouTube released for MySQL sharding, or another good open source solution is a proxy SQL, which often can help you to implement sharding. We also see a lot of tools exist out there. Well, if you look at the Memcache and Redis, they also have some sharding solutions which you can do for them as well, because frankly, Memcache and Redis, they are also evidential single node applications, or you can use the same solutions as I mentioned as MongoDB and Cassandra, which while they don't have a lot of features of relational databases, they often allow to solve the sharding problem much nicer. Analytics. Well, for analytics, OLAP, complicated queries, you know, big data, there is a lot of words which are can be used to describe this kind of area. And I think in this case, MySQL is not really set up for running complicated queries, crunching through a lot of data and scale. There is a lot of limitations out there. MySQL doesn't have, for example, column-based storage engine. MySQL optimizer is quite limited, right, to relatively basic query basic query execution strategies. MySQL executes single query in within a single thread. That means it doesn't really scale even among the multiple CPU cores on the single system. And of course, it also does not do distributed query execution, which can use multiple nodes. So what are solutions out there? Well, frankly, that is where there is no very good solution inside MySQL. If it is kind of a small to medium scale, let's say you just need reporting which crunches through 1 million rows or so, right, or maybe tens of million if it's not real time, then we can do a lot through schema configuration, and schema design. But if you are really looking at some very robust, large-scale data processing, we see a lot of external solutions being used, such as Hadoop and Spark, right? Or if you're looking at other solutions, Vertica and ClickHouse, another solution which we see quite commonly. Full text search is another common issue which we see. With MySQL, it can handle basic full text search, but doesn't scale well with the data volume. Again, it's unable to do parallel processing. It's limited in sort of how it can you can control full text search relevance, and it's also hard to do some common full text search needs, such as integration with GIS or facets. It also doesn't do any language processing, you know, so, or any advanced ones, such as stemming, understanding synonyms, understanding what the things are in the same sentence and stuff like that. What are solutions out there? Well, in MySQL, I think a built-in full-text search, which is finally available for InnoDB started MySQL 5.6, is actually good for small scale search applications. If you just want to build a search at basic search at a few gigabytes of data, MySQL can work reasonably well. If you are looking for some advanced search solutions, we see Elastic, Solr, or Sphinx being used in this case. Now, what is important though is the open source ecosystem is always evolving. And I think if you are really serious about having a great system build and finding efficient solutions, both in terms of development pains, right, making it easy for development team to produce the new features, as well as operational efficiency, and as easy to manage, as well as resource utilization, then it's good to be always on the lookout for better solutions. And today, Nikita Ivanov will show you what exactly you can do with this relatively new solution, Apache Ignite. Well, let's welcome Nikita here.
Thank you, Peter. Welcome, everybody. Thanks for joining this webinar. My name is Nikita Ivanov. I'm a founder and Chief Technology Officer of GridGain Systems, and also was at the beginning of the Apache Ignite project. So what I'm going to talk today about is give you a very quick overview of what Apache Ignite is and how it pertains to some of the interesting use cases that Peter mentioned in terms of the really handling a high-performance data or a large data scale processing, or some of the maybe OLAP scenarios. So what I usually do before I talk about anything about a product, I always give like a couple of minutes introduction. What is in-memory computing? And not much about what it is, but I'm sure most of you probably have an understanding of what it is. But why all of a sudden you're probably hearing it in every corner? Why is it in-memory computing such a powerful concept right now? And jumping ahead a little bit, GridGain and Ignite, and we're talking about Ignite today as an open source project, is in-memory computing platform. So in-memory computing is nothing new, right? We've had this idea for the last 30, 40 years. The minute somebody developed a idea of caching, storing data in RAM, and then on a slower disk, memory computing was born. And the whole idea of memory computing fundamentally is all about, can we store data in RAM? Because RAM is dramatically faster, that's where instructions being executed, than on the disk. Because every time we need to access data on the disk, we have to load this data from the disk to the RAM, do something with it, and drop it. So why not keep it in the RAM so we can save on this, trips to disks? And that's all there is to it. Idea is very simple. It's been, as I mentioned, literally, closing on half a century by now, on when the first kind of in-memory processing came around. What was really changed in the last, let's say, 5-7 years is that two trends really collided and really kind of picked. One of them, obviously, is the demand for real-time data processing with the conjunction of growth of data. Again, I don't have to tell you this. You guys already know this stuff. I mean, I always, when I present about it, I always ask my audience, what was the last time you've seen an iPhone app where you click a button and it tells you back, hey, we're going to email your result tomorrow because we have overnight processing? It just never happens. Any apps you use today, social or enterprise apps, they all have instant response. But behind those instant responses, ever-growing data sizes. And in-memory computing is about the only technological answer to speed up data processing. There's, what I also basically keep saying is that if you think about in-memory computing, we went through this whole kind of historic evolution. We went from tapes to disks. In the mid-70s, the IBM Winchester systems really revolutionized the pricing of the disks, and then early 90s, the flash came around, and now flash is the predominant storage for a lot of our data. And then we moved to memory, and I always keep asking the question, what's next? Think about it. What is the possible next storage layer where we can keep our data? And as long as we keep our current architecture of computers as we know them from the beginning, there is no next. I mean, yes, there is a on cache CPU, on CPU cache, but it's very small due to physical limitation. It's only about 2-3 times faster than the modern DDR5s. So fundamentally, in-memory computing is the last frontier in actual storage technology. And with advancement of new memory, such as non-volatile memory, if you ask any analyst, predicting that in the next 10-15 years, we're going to, literally migrate into the in-memory storage as the predominant pattern, and we'll use disks only as a historical backups. So another, by the way, on the right side of the slide, you can see another interesting trend that contributed to the excitement about memory computing is the price. Naturally, the biggest roadblock was always the pricing. Memory was always costing a lot more than disks. Disks today, especially spinning disks or spinning rust, as we call them, literally free today. Flash is not free, but the spinning disks are literally free. Memory is still more expensive. But if you can see this diagram, it's probably hard to see, but what you can basically see from it is that the price of RAM declines in the same way, in the same trend as the price of disks. It's still more expensive, but it's still declining literally about 30% every year and a half, something like this. And about 5 or 7 years ago, really the pricing became kind of, it kind of broke through a certain level, and it became quite affordable. I always keep saying that today a terabyte of RAM in a cluster costs about $20,000. So I always bring up this comparison that about a few years ago, the entire working set of Twitter was about 7 terabytes. So basically all your tweets, all your metadata for about 1 week was about 7 terabytes. So for the price of well-loaded Tesla today, you can buy enough RAM and processing capacity to hold the entire Twitter working set in RAM. So the RAM is still expensive, but it has become majorly affordable for a lot of different businesses. And so when these two trends combined, the growth of rather in demand for real-time processing combined with a declining DRAM pricing, that's what really triggered the kind of renewed interest in a very old technology. And we see in a lot of projects, like Peter mentioned, the Redis and Memcached, and Apache Ignite, and Apache Spark, and every imaginable database now has memory options and whatnot. That's what's really behind that. Another interesting, while we're on the slide, just one more remark. Another interesting, kind of follow up on one of the slides Peter mentioned. Another interesting, a property of a memory systems, which is fairly unusual if you just, come new to this, is that all of the memory systems are distributed by nature. And that's something that's fairly, surprising for a lot of people. Like, why are we talking about distribution when we're just talking about storing data in RAM versus disk? And the reason for that is that from a day one, literally, go back 40, 50 years, it was almost impossible to keep all the necessary data in a one computer. If you don't have to go back 40 years, if you go back 20 years, there was a 16-bit CPUs. We could only have just about 1 gigabyte of RAM. But disks were pretty large, especially tapes were very large. So from a day one, in memory systems were designed to be distributed, so we can actually create a cluster of computers. Sometimes, our project, like Apache Ignite, runs on over 2,000 nodes in some of the clients, that they can basically, collect the memory from all those computers, create this virtual bank of RAM. And then you have the total capacity that actually is fairly usable and fairly useful. And I always keep saying that, surprisingly to a lot of folks, memory systems today, memory platforms, are one of the most sophisticated distributed systems in existence. Because for memory systems, it was an absolute technical necessity to become very efficient, very well-architected distributed systems first, before they ever become a memory systems. Because without that, they would have no use. And literally, if you look at one of the largest installations of, let's say, Apache Ignite, it rivals installations of Cassandra and Hadoop with multi-thousand nodes clusters that are in production today. So let's talk about what Apache Ignite is. Apache Ignite is a memory data fabric, or sometimes we call it a memory data platform. And it's really, it's a lean open source, we call it a cloud-ready distributed software that provides a significant performance boost and scalability by keeping data in memory across large sets. Sometimes it could be large, sometimes it could be less, just a few nodes, literally. But typical installation for us would be somewhere like, 8, 16, 32 nodes. So fundamentally, memory data fabric is the layer that slides architecturally between your data sources and your applications. And here's another very, I'm sure it's a fairly unusual kind kind of characteristic of memory computing. So people constantly thinking in memory computing, I probably have to keep my entire data in RAM, and I have to get rid of databases. Well, nothing can be further from the truth. As a matter of fact, most of the memory systems work essentially as a sophisticated caching layer on top of existing databases. Yes, sometimes you don't have to have database at all. You can keep the entire data in a memory layer, and Apache Ignite provides all the same properties like traditional databases, like your full transactional ACID capabilities, durability, high availability. But the world of database doesn't go anywhere. It's here to stay. It's a fundamental system of records. And what systems like Apache Ignite really allow you to do is allow you to slide in between your applications and your databases. And it's this layer that provides the high speed and high scalability for the data you can store. So in many cases, let me just, since we only have kind of a short conversation, in many cases, the use case for the whole thing is very simple. You have existing database, and you faced with one of those use cases that Peter just described. You either have to have a high-speed data processing, so you have large data sets that don't fit one instance, or you have some OLAP queries and whatnot. And you really, database is not really a great choice because it was clearly not designed for it. Just, it's a very much, when Peter said not designed for it, it's a very smart comment because we tend to, especially here in Silicon Valley, we tend to, get on the bandwagon and really misuse a lot of technologies. Like Hadoop, for example, was initially, the first couple of years, was used for a lot of transactional payloads, and it was extremely painful to do that. So Spark, for example, people forget that Spark has no transaction. SQL has no indices, for example. It's very easy to misuse and get wrong results. So you have to use technology properly. And so Apache Ignite really allows you to slide in between your data sources in your apps and really provide you the speed and scalability. It provides you speed by allowing you to keep data in RAM in a cluster. And obviously, access to this data and processing in place is dramatically faster than SQL. And it gives us scalability or scale by distributing this data across a large cluster of computers, as much as you can basically put in. And that gives you this, classical parallelization of processing, which leads to much better scalability. At the same time, Apache Ignite is a fairly mature and a fairly feature-rich system. Unlike, Peter mentioned a couple of examples like Redis and Memcached. Those are predominantly key value systems, right? They're essentially a key value store that sits in RAM. And some of the technologies that we have obviously have this as well. So traditional in-memory data grids, and I'll talk about it a little bit later, is essentially a kind of a key value store on steroids. But we also have a traditional SQL access. So if your applications, for example, talk to a database through SQL, you can basically have a zero change. You can continue to talk SQL to Apache Ignite, and we'll take care about the parallelization of a SQL. We have very nice, very advanced, and constantly improving SQL support. SQL 99 is the standard we support. So Apache Ignite is one of those in-memory systems where you can definitely use the key value store or any other functional components that we have, and I'll talk about the next slide, but you can basically just use what you've been using before. You can use SQL and to access and process the same data, but you can basically process in RAM. So let me talk about some of the major components that we have on Apache Ignite. So the reason we call this fabric or a platform is for a reason. From a get-go, and I was at the very beginning about 10 years ago when I wrote the first line of code for Apache Ignite, from the beginning the idea was that in-memory processing is a really new paradigm, and we don't want to create a one-trick pony. We've had caching systems before, distributed caching, but we've seen that we kind of foresaw the idea that the use case will be dramatically more than just a basic key value like distributed hash map. And that's how the Apache Ignite really grew. We have many different components or functional areas, if you will, in the project itself. So we have a data grid, which is traditional transactional key value store. We have a compute grid in it, in Apache Ignite. A compute grid really is all about a traditional HPC, high-performance computing. Essentially, it's a fancy word for parallelized processing, something along the lines you can do in Hadoop as well. We have a service grid for kind of, a declarative service orchestration on a cluster. We have very advanced streaming capabilities, so you can stream data into the system and have window-based processing and whatnot. We have a very nice integration with Hadoop and Spark, by the way, as a kind of, components in the project. So if you have Hadoop installations, that can help there as well. We have very advanced clustering. Remember I mentioned to you that in-memory systems is one of the most advanced distributed systems. Again, it's not just a statement. It is literally a fact of life, because systems like this have to be distributed system first before they become in-memory system second. Another area that's very interesting, we have a full-blown HDFS compliant file system in memory. So if you just want to open files, store files, and essentially have a normal file system in RAM, you can have it. Naturally, you get tremendous performance benefits of that. And by the way, with HDFS scenario, this file system can act as the caching file system on top of the disk-based HDFS. Very interesting use case. We have very interesting messaging, and we have events obviously in the system, so you can listen to different things happening on the cluster and whatnot. We have actually an interesting data structures. If you just programming in whatever language you're programming, and we support quite a few of them in Java and all the JVM languages like Scala and Boolean Java. We also support .NET stack, and we support C++ stack. So we have interesting data structures where you can basically just take your traditional data structures like lists and queues and hash map and dictionaries, and literally convert them to distributed data structures. So that if you, let's say, working with hash map, all of a sudden your hash map can store petabytes of data because it's fully distributed and you can work on it. So there's two technologies that actually are really near and dear towards the topic we're discussing today. How do we accelerate payloads from a database? And typically, most of the time, it coalesces around two things: compute grid and data grid. And this is basically what I want to talk about it now. So what is if you look at Apache Ignite, they're probably two of the most important components that you're going to use almost on a daily basis is naturally these two: in-memory data grid, in-memory compute grid. So what is in-memory data grid? You probably heard this term. But fundamentally, it is essentially distributed in-memory key value store. That's what it is. There's a lot of characteristics about data grids in general as a concept, and I'm kind of listing some of those that actually exist in Apache Ignite. So first of all, it is essentially a key value store. In Apache Ignite, it's a fully transactional key value store. The really great architectural decision we made early on years ago is that we didn't go the route of eventual consistency. Because with eventually consistency or eventually consistent transactions, you can never get to a normal asset properties. You still get a good read and write performance, but you can never get, even a full quorum, by the way, you can never get a normal consistency that you really expect from, or used to expect from system like database or DBMS. So we went a different route. We actually implemented a fully ASIC compliant transaction management, distributed transaction management, and I keep distributed every time, but it's almost default in the memory systems. But we also allow for relaxation of the asset properties, so you can get back the performance. If you don't need a fully ASIC overhead on your operations, you can, for example, switch to asynchronous commit protocol property and gain back most of the performance you naturally lose with a very rigid ASIC compliant transactions. So we support both on-heap and off-heap. It's a very much Java-related issue, but in Java world, if somebody working with Java, you probably know that Java is very good for on-heap, basically whatever memory is managed by Java. But typical today, Blade can have 64, 96 gigabyte of RAM, and Java is not really good at it. So we have our own system to basically take advantage of entire physical memory on a hardware. So we have a high available in-memory replicas. People always ask, how do you guys deal with the data in RAM? What if I unplug my computer? Well, yes, if you don't have any replicas, you unplug your computer and you have not a database behind this to which we synchronized, yes, you're going to lose your data. And often, that's perfectly fine because data is transient. But if you need to have a certain guarantees, we provide a multitude of options how you can provide multiple lines of uptime and data safety. So you can have multiple replicas of the same data in the different parts of the cluster. So when not one node goes down, data is not lost. If you have existing database like MySQL, we can sync up with this database both synchronously and asynchronously, so you don't lose the data at all. Obviously, many of those solutions or options rather have certain performance penalty, but the good news, you are the controls. You can choose for any particular data set. We call them caches. You can have hundreds of different caches within the system, all configured differently. Some data sets can be completely transient. You don't care if you lose it. You need high performance for them. Some data sets have to be completely transactional and synced up to database, like your account data or balances and whatnot in the financial systems. You can do all of those. I mentioned that we have distributed asset transactions, and again, it's a very important property, and I cannot emphasize it again and again, because most of the NoSQL storage systems and most of the memory systems today are not asset compliant transactions. You cannot get the same transactional behavior as you get from your MySQL. We at Apache Ignite have a fully asset transaction, so you have the same isolation levels. We have both optimistic and pessimistic transactions. We have both, a normal two-phase commit protocol that you can use. I mentioned a couple of minutes ago, we support full SQL 99 with both GDBC or DBC drivers. So again, that's one of the great features of Apache Ignite. If your applications talk directly to database today through SQL, you can continue to use exactly the same language you love to learn, you love to use, SQL, and you can basically query the data in RAM using the same SQL. It's not some kind of a half-ass approach solution like, for example, in Spark. We have a very advanced indexing. We use H2 as a SQL optimization engine on each node, and we get a very good performance in our SQL. And just a quick comparison, we're about 100 times faster than a Spark SQL, basically SQL on Spark. And again, not because we're any smarter than Spark folks, we love the project as well, but that's the difference in architecture. In Spark, it's very hard to get indices properly done. In Apache Ignite, that's what we accomplished. Another interesting story about a data grid is that I always keep saying that you store data somewhere, right? For whether you store it in MySQL or whether you store it in Apache Ignite or in both places, you're not storing it for the sake of storage, unless you're in the backup business. You're always storing data for one reason, to process it. And that's where the systems like Apache Ignite, in generally in-memory computing systems, are much more advanced, or at least have to be much more advanced than traditional databases. Because in traditional databases, you're pretty much limited to either SQL or store procedures. That's pretty much all you have. With whether it's a MySQL or Oracle database, it doesn't really matter. You basically limited to that paradigm. In memory systems, not only have the same SQL if you use Apache Ignite, but you have the entire option of in-memory compute grid, which is a collection essentially of 3 or 4 different paradigms of how you can process data in parallel fashion that you have in memory. So our memory compute grid is essentially how that's a one component with which we started many years ago with Apache Ignite. And it has grown into one of the most advanced HPC platforms today in existence. We support at least 4 or 5 different paradigms of how you can process that. So we support very fundamental kind of the MapReduce style of processing, which is we support both MapReduce compatible with Hadoop, and we support much more, in my opinion, optimized MapReduce or fork and join type of application. We also have support for MPI, traditional MPI processing, or with message passing. We support simple RPC protocols and whatnot. So you can basically do any kind of processing of the data or just the computation. Sometimes your computations are very much transient. Very classical example, your Monte Carlo simulations. They don't really have much data, but it's a very intensively compute job. And it's one of those things you cannot really do well in SQL at all, because SQL was never designed for it. But with Apache Ignite, you can do it beautifully. You can run, within half an hour, you can develop the code that runs on thousands of computers in parallel and gives you the Monte Carlo, any kind of, linear algebra vectors very easily. And by the way, this is the great place to start with your machine learning and whatnot. So our compute grid is actually, there's a list of kind of laundry list of features here. Some of them will sound a little bit technical if you're not familiar with Apache Ignite, but it's a very advanced system. We took care about, deployment problems, but if you ever work with distributed systems, you probably know that one of the biggest problems in distributed systems is really a deployment. And because you have literally, sometimes tens and hundreds of computers, and how do you deploy all this, updates to the code and whatnot on all those different nodes. In our system, you basically don't. We have a completely automated way of how deployment works. We have, if you guys are familiar with Java, we have, very advanced class loading architecture where we can load classes on demand throughout the cluster. You can schedule, you can run tasks on demand from code. You can schedule tasks in the cron-like. We have very advanced, management capabilities there. We have state checkpoints. If you are running long tasks that, let's say, take an hour, one of the biggest problems with the long-running task is that the task fails, or during the development, when you're constantly debugging a task, you have to constantly restart it from the beginning, and that's a pain. And we have a very elegant solution with the state checkpoints. So let's say if the task runs for an hour, you can stack checkpoint it every minute, and the next time you want to restart this task after a failure or after some debugging, it can restart from the latest checkpoint. Very simple, very elegant, and it's really beautiful when you run long-running tasks. Naturally, like in a memory data grid and compute grid, we have automatic failure, automatic load balancing. Those things count by default. And naturally, with the memory compute grid, we have a full cluster management. So one of the interesting things about Apache Ignite, and that's a very unique, let's say, well, it's very unique to Apache Ignite, as a matter of fact, is that we don't really hide the clustering capabilities from you. If you're familiar with distributed systems like, like a Zookeeper that's used in Apache Spark and Hadoop, it's really a thorn. It's really a different system. It hides all the details from you. You have very just high-level APIs and whatnot. And in Apache Ignite, I would always keep interesting to me that kind of learning that roughly about 20% of our users in open source community really using Apache Ignite just for clustering capabilities. Because we beautifully work anywhere from a single laptop to an in-house data center, to Amazon, Azure, SoftLayer, Google Computer Engine, everywhere. And it literally requires nothing from you. You just basically, like on this laptop I'm doing a presentation right now, I can launch 1, 2, or 100 nodes. As long as I have enough RAM and CPU capacity, I can launch the entire cluster right in the same laptop and debug all my algorithms. That's going to work exactly the same way as if you launched on AWS, for example. So the clustering capabilities are not just a footnote. They're a bona fide first-level API. And as I mentioned, in a good portion of our users just use Ignite for its beautiful clustering capabilities. I always keep saying there's literally, if you download Ignite, 5 minutes later you have a cluster on your laptop. 2, 3 nodes, as many as you like to start. It's very simple, very elegant. So in the last few minutes we have, if I'm not mistaken, let me just give you one example of the company that was kind of interesting. So we work with a company called Silver Spring Networks. It's an IoT company. It's a very interesting use case. Along, by the way, exactly along the lines of the use case that Peter mentioned on his presentation. And it's a very typical use case for us. IoT is actually very large and growing industry, sector industry, but it was a very traditional use case where they had a system in place, and that system actually was working with databases. And what Silver Spring does, it basically installs the energy meters or power meters at your home. And as you can imagine, they literally sign up a major contracts and they majorly expand it. They have millions of homes now with a meter installed. And this meter, transmits a lot of information, as you can imagine. And the original design they had for the system was choking up because, it was a lot of updates, in the same time, a lot of reads. Because not only you have to basically collect all this information, you have to do some in-stream processing of that because you have to see, all this, kind of spot metrics and whatnot. But you also have to store this information for a lot of compliance regulation reasons and whatnot. And then you have to, at the same time, read this information for the last week, for the last months, to do any kind of, this multi-business, operations like, billing and analytics and, and spot pricing, and it's a very complex business. So fundamentally, they basically thought that the existing database was not going to perform. But in the same time, they don't want to, completely throw it away, because that will require a complete redesigning. What they've done is very unique. They kept the database almost unchanged, because database is where all other systems get connected to. But they put the entire cluster of Apache Ignite and GridGain, as a matter of fact, on top of that, and that provided this layer of speed and scale. The layer that, they can scale as much as they need. They can literally just add nodes to it, and grow from 100 to 1,000, literally, as long as they can add hardware to it. And nothing's going to change to the software that's run on it, except it's going to work faster and faster and faster. And they also basically gain the ability to store roughly about a week of data entirely in RAM, and has an absolutely blessed speed to access it, to process it, to look at it through and whatnot. They still basically have some of the kind of a hacks, if you will, where if they need to query a large data set, let's say do the query for entire year, they're not keeping the entire year in RAM. So they have to do multiple queries, one for RAM, one for the disk, and collocate results. But those are very far in apart. But fundamentally, with introduction of Ignite as a layer on top of the existing database, they were able to basically scale very nicely. What's really cool, and that's a real big difference between traditional databases and systems like Apache Ignite, is the database is hard to scale. And Peter made a great comments about why. Because some of the most advanced ones, like even MySQL, which is, in my opinion, one of the most advanced databases in existence today, they're not designed for the scale. They're not designed to run on, on hundreds of nodes, because SQL is not really designed for the parallel processing due to joins limitation, right? You cannot really do joins in parallel very well. But the systems like Apache Ignite are designed for a massive scalability. So you can basically combine the best of two worlds. You can keep your existing database as it is, literally with very minimal, if any, changes whatsoever. You can add the layer of Apache Ignite and gain this high performance and high scalability environment in which you can keep at least a portion of your data. In this case, really a portion, because data that Silverspring was accumulated really humongous. And really gain speed and performance. That was a pretty successful project for us. It's a client for us now. And was very, very proud of this use case. So that's all I have from my side. Alyssa, probably back to you.
Okay, great. We do have several questions, and I just want to assure the audience that you will get a copy of the slides as well as a link to the recording. I'm going to go ahead and try to share my screen. And guys, if you can just let me know that you can see my screen, that would be great. And give me 1 second here. And let's see. Can you see my screen?
I can see your edit.
You can see my edit screen.
Yeah.
Okay. This is the problem that we had before. While I fix this, let me go ahead and ask the first question. You made a comment about sliding it in, slide Apache Ignite in. How much rewrite is required of the application code?
There's always some rewrite. It's never like a complete slide in. Let's be clear here. It depends on what interface you use to interact with database, or your data access layer, if you will. So if you use just SQL and nothing else, then your quote-unquote rewrite will be very limited. So you do have to basically understand what portion of the data will go to the memory. I always say don't put everything unless you have a very small data set, like a few terabytes. If you have hundreds of terabytes of data, don't do all the memory. You don't have to. Just look at your working set and put your working set in RAM. But then, that's kind of more of a DevOps question, literally. You can, preload this cache or keep this cache warm or do the warm up on demand. But then fundamentally, your apps just have to issue a different SQL query, maybe through a different JDBC string or DBC string. So that's a fairly limited array, and we're talking about maybe a few weeks for a large application. And we've done this many times. So if it's a SQL-only app, in a few weeks we can actually convert some of the banking applications. If you guys use something more sophisticated in non-SQL, then the rewrite will be a little bit more significant, because we support key value access, we support transactions, we support SQL, but if it's not in one of those, it's something you guys develop in-house, you have to find a way to integrate us. Typically, in these use cases, we're looking at, I don't know, months or 2 or 3 of work for 1 or 2 engineers. So that's a typical kind of a scale. And obviously for greenfield applications, which you're developing from scratch or developing anew, that's not an issue, because you can pick and choose what the data access layer would be.
Okay, great. Hey guys, I can't see the questions while I have the slide up. So Nikita, would you mind if I changed you back to the presenter?
Sure.
Okay, great. I appreciate that.
I'll keep this slide over.
Okay, give me 1 second here. All right. Sorry about that, audience. Just gotta love technology. All right, so the next question is, what preparation do you recommend to my MySQL infrastructure for optimal Apache Ignite benefits? And is that something Percona can help us with?
Absolutely, Percona can help, and Percona is the leader in this space. There's no question. Surprisingly, there's not much preparation needs to be done. You still need to do your typical database tuning and optimization like you would do without Apache Ignite, because the better and faster SQL works on MySQL, the better and faster Ignite will work as a layer on top of it. Maybe there is, I always keep saying there's no generic recommendations. You run your tests, and you basically have to figure out, if certain tables get hit many times, you optimize that. But fundamentally, we've seen dozens and dozens of projects where MySQL was the backend in applications where Ignite was used. I cannot recall a single time where we had a major issue of compatibility between Ignite and MySQL. In many ways, it just works.
Okay, Peter, did you have any comments as well about that?
Yes. I agree with Nikita. I think it's in this case for MySQL, you still want to follow the best practices. In this case, the performance tuning, havability, right? Making sure you are taking backups and all this stuff. Especially if you're planning to run Apache Ignite alongside of MySQL, for example, as a cache, and still keep MySQL as your primary data store.
Okay, the next question is, what security options such as user authentication, authorization, data encryption at rest does GridGain implement versus what is in native Apache Ignite?
That's a good question. So in Apache Ignite, let's put it this way, there are interfaces on Apache Ignite that you can implement yourself. And I think there's quite a few things actually available in Apache Ignite, like encryption for CPIP communication. But in one of the options in the GridGain is much more kind of robust security and encryption implementation. So not only we have a full audit for the data in GridGain, there's quite a few implemented components for integration with Kerberos, for example, key management, and for encryption and authentication. But there is definitely authentication, for example, between clients and servers that's available in Ignite, sure. But I think the biggest addition that GridGain brings, which is essentially enterprise edition of Apache Ignite, is the audit capability. Because if you guys in financial service industry, you know how important to have an audit on the data, because that's your compliance regulations require.
Okay, the next question. How does this support the relational objects in memory cache? If yes, then how will it manage the invalidation of the in-memory data objects?
So if I'm guessing the question correctly, we essentially keep the data in RAM always as a key value store. But then the beauty of a key value store is that it's very malleable. You can really view it as, let's say, the file system, where every cache is a file, and essentially you have a file of key value pairs. At the same time, you can keep this key value store. You can view it as a SQL store, as a relational database. And that's exactly what we do. So it's one of the really unique capabilities of Apache Ignite is that you can store that as a key value and then immediately exit as a file or as a SQL database. So, and that's very unique. I'm not sure it's widely used, because it's why would you do this, right? But there are some use cases where it's actually fairly interesting, especially for legacy applications, where you can store data as a file. For example, you literally open file, write something, close file, and then the very next line of your code, you query this file, quote unquote, with a SQL. It's the same data, we're just giving you different views on the same data. As far as your second part of the question, invalidation, if I'm guessing you're right, you're talking about how do we invalidate data in RAM when it gets updated in database externally. So that's a hard question, first of all. And it's a hard, it's not a question, but it's a hard feature, because we typically recommend that all updates to database go through Ignite, because this way we know what's been updated in database. We can smartly, obviously, invalidate data in RAM, so keep it in sync. If it's not possible, then we have solutions like a Oracle Golden Gate product, which we have integration in Enterprise Edition, that basically allows us to have essentially think about it as a callback from a database. When something gets updated in database, we get a logical callback to our application, and we can invalidate the same entry in cache. But again, that requires Enterprise Edition. That requires a Golden Gate product from Oracle to have in place. Elisa?
Sorry, I was on mute. How are the query optimization options present in Ignite?
Well, as I mentioned when I was talking, we actually made a very interesting decision. We decided not to implement our own SQL optimizer and everything else, because it will take years to do it right. Just look at MySQL and Postgres and everybody else. It took them years and years. So what we do, we use on each node in a cluster, we use a localized H2 database engine that, in my opinion, does a very good job for a local and execution plan optimization. What we added on top, the whole distribution of SQL processing. So on each node, we use a proven H2 database instance that basically manages all the actual localized SQL execution. And Ignite provides all the distribution logic for how do we distribute the SQL processing, how do we collect results back, and whatnot. So that, I guess, why we're literally a predominant SQL engine when it comes to memory systems, because we smartly decided not to reinvent the wheel and use something that is available and proven, and really add only where we can add benefits like distribution and parallelization.
Okay, well, that brings us to the top of the hour. Actually, we're a little bit over. And I would like to thank Peter and Nikita for a great presentation. Also, Percona would like to extend a special offer to webinar attendees. Percona Live is a very large MySQL, MongoDB, and open source database conference being held the 24th through the 27th of April in Santa Clara. And I will send a special code for you guys when you register to receive a 10% discount as a thanks for attending this webinar. With that said, Peter and Nikita, thank you so very much. And everyone, I will be sending the recording and the slides to you after the show, and we hope to see you in a future.
Thank you very much.
Thank you, guys.